Okay, let's start with the first one. Oops, a little black marker, there we go. Our amplitude, of course, is absolute value of -2. Remember, your amplitude itself is always a positive value. So that's going to be 2. But of course, keep note that you do have a negative sign graph here. So from our intercept, instead of going to a maximum, we're going to first go to a minimum. Our period is going to be 2 pi, because that is the standard period of a sine graph, over the b value. Your b value here is 1/2. So 2 pi over 1/2 is going to equal 4 pi. So you have a large period. And that phase shift, which will give you your starting point, is going to be b over, or I'm sorry, c over b. So it's going to be pi divided by 1/2, and that's going to be 2 pi. So it's going to shift out to 2 pi and have a period of 4 pi. So when we think about this graph, this is a negative sine function. Negative sine functions, let me get a better pen, hold on, there we go. Negative sine functions from your starting point will go down, hit an intercept, hit a max, and then hit an intercept again. So our starting point is our phase shift, and that's going to start at an intercept. So that's going to be 2 pi, and since it's an intercept, it has a y value of 0. Then it's going to come down to a minimum, will be our next point. Now, recall, what you want to do is take this period, divide by 4 to get your 5 key points, and you're going to have a key value every pi. So our minimum is going to occur at 2 pi plus a pi. That's going to occur at pi 3 pi. And since it's a minimum, your amplitude is 2, it's going to be at -2. Then you're going to hit another intercept, of course. That would be 4 pi. And that's an intercept, so it's at 0. Then it's a max at 5 pi. And that's going to be +2. And then sine graphs end, or one phase of a sine graph ends on an intercept. And that's going to be 6 pi. 0. Double check yourself. From your initial to your end should be a distance of 4 pi, and 2 pi to 6 pi does have a distance of 4 pi. So the graph of this, I know I don't really have much room for a graph on this particular paper, is simply, you need, I'm going to call that 2 pi. And all you really need to do is label, this is 6 pi to -2. It's going to come down, go up, and go down. It will continue, so keep the arrows and do label each of these points. So whether you label them here, intercept, min, intercept, max, intercept, that's fine. If you do not create this list, please be sure to come over here to the graph and write like 3 pi -2. You know, put all those 5 points in the graph if you do not list them. But I do need to see a graph. I need to see these points of 2 pi, 4 pi, 6 pi at the very least. And label as much on the graph as you can. All right, let's do cosine. So amplitude here is just the absolute value of 1 is 1. Your period equals 2 pi over 3. right? Can't really do anything other than that. And phase shift is none. There's no C value, so there's no phase shift. All right. So here we got to do this one is a little more difficult to work with the fractions, but let's take a look. So my period of 2 pi over 3 divided by 4, well, isn't that 2 pi over 3 times 1/4 equals 2 pi over 12. So this is a cosine, it's positive cosine. So recall your positive cosine, we want that point. Here are our 5 key points, right? Max, intercept, min, intercept, max. So we start with a max. There is no phase shift, so our initial value is going to be at 0. If there's no phase shift, you go back to your standard cosine graph, it's going to start at 0. And the amplitude was 1, so it's 0, 1. Now, what we're looking for is our next value, which is an intercept. And I need to add 2 pi over 12. I'm going to keep it unreduced for a moment because it makes it a little bit easier. I'm going to add that 1/4 pi, right? So I'm going to get 2 pi over 12, comma. Oh, it's an intercept, so it's 0. So again, I have max, intercept. Now I need a minimum value. I'm going to add another 2 pi over 12. So again, I'm keeping them not reduced right now. It just makes it a lot easier to do the additions. So another 2 pi over 12 is 4 pi over 12. And that's going to be a minimum. That's at -1. Next point's an intercept. Add another 2 pi over 12. That makes it 6 pi over 12. It's an intercept. And then we end on a max, which is another 2 pi over 12. So now we're at 8 pi over 12. If you keep it unreduced fractions, look how easy it was to add. Keep adding 2 pi over 12. And that's at 1. All right. Okay, so here's what I want to show you. What was our period? 2 pi over 3. 0 plus 2 pi over 3, right? Well, 8 pi over 12, you divide by 4, reduces to 2 pi over 3, is indeed 2 pi over 3. When you put everything on the graph, this is a good time you can actually reduce those fractions. So this, of course, is 0, 1, right? I'll draw my graph. I know what it's supposed to look like. I'm going to keep it continue. You never end it. Okay, so 2 pi over 12 is pi over 6, 0. My minimum value is pi over 3, -1, right? Because 4/12 is 1/3. My intercept is 6 pi over 12, so that's 1/2. That's pi over 2, 0. My maximum value is 8 pi over 12, which of course reduces by 4 to 2 pi over 3, which was our period from start to finish. And there you have your cosine 3x graph. Okay, let's go to the next one. And this is my tan. So amplitude -1 is 1. We do have to keep in mind that this particular graph is negative. So where you're classic, you just think about what happens between those asymptotes. Classic tan goes like this. So your negative tan graph is going to go on this side. Okay, so next we have our period. And of course, this is now a tan, so you just do pi divided by the b value, pi over 4, and that's just pi over 4. So every pi over 4, you will see one of these tan functions, one of these cycles of a tan graph. The phase shift is really going to move this graph. So the phase shift is 2 pi over 4, which is pi over 2. But it's actually negative 2 pi. So remember, your standard equation would look like this. So the standard function has a negative. So when you see a positive here, this actually means minus negative 2 pi. So you got to use negative 2 pi, which then creates this phase shift of negative pi over 2. So tan works a little bit differently than, say, your other functions, because all you really have on your tan graph that we're going to actually graph is our intercept and then the asymptotes around that intercept. So this here is your new intercept, where you would normally have this value 0. We need to go find negative pi over 2. So when you go and draw your graph, actually, let me change that a little bit. Right, boom. I'm going to put negative pi over 2 out here. All right, so our graph is going to definitely cross here. What we need to get are the intercepts. Half the period is in that direction and half the period is in this direction. So instead of taking our period and dividing by 4 like we did in sine and cosine graphs to get those 5 key points, well, you really only need 3 key points in a tan graph: where the asymptotes are and where the intercept is. So in this case, we're going to take it and we're going to divide by 2. So take pi over 4 divided by 2, which is times 1/2, which is pi eighths. And that makes sense because 2 pi over 8s make a pi over 4. So we're going to go pi over 8 in one direction and pi over 8 in the other direction. Remember, this is a negative value. So when you add pi over 8, well, you got to put it over 8, so it becomes negative 4 pi over 2 plus pi over, negative 4 pi over 8. That's going to give you an asymptote at negative 3 pi over 8. And then when you subtract, it would be negative 4 pi over 4 minus pi over 8. That's going to give you an asymptote at negative 5 pi over 8. And then your graph come up and go down. So the equations of your asymptote are x equals negative 5 pi over 8, x equals 3 pi over 8, with an intercept at 0, at a negative pi over 2, 0. Okay, so there's your tan function. And this next graph, all I would like you to do is, if I give you the cosine function listed below, can you write the exact same secant function, the reciprocal function? So for this particular problem, what you're really looking to do is think about, okay, first I need those asymptotes. Asymptotes are going to occur because it's a reciprocal graph wherever your cosine graph is 0. So there's an asymptote, asymptote, asymptote. Okay, and then it becomes these. So reciprocal just looks like this. And it says to label any max min, so you should very easily be able to label max mins and asymptotes. Asymptotes are equations. They are labeled with x equals 0, x equals 2 pi, and this line is x equals 4 pi, x equals 6 pi. Asymptotes are equations of a line. Max and mins are point values, so sorry, this first one would be pi, comma, 0.5. 3 pi, comma, negative 0.5. And 5 pi, comma, 0.5. So I do want you to label the asymptotes and the max and mins for this particular graph. Okay, let's move on to the tan and cotan function. So again, we're going to follow the same idea of a reciprocal function, and the easiest thing to do first is those asymptotes. So in your tan graph, wherever you have an intercept, the reciprocal graph is going to be an asymptote, because when you take the reciprocal of 0, it's undefined. So everywhere you have an intercept, you draw an asymptote. And label it. It's always x equals. Every horizontal line is x equals whatever the intercept actually is. So x equals 2 pi and x equals 0. All right. Where you had an asymptote on your tan function, so even though you can't see it, the tan, it's not drawn, the tan function has this yellow line, which is technically an asymptote. For the cotan, that's going to be an intercept. Where you had an asymptote is going to be an intercept. Now, cotan goes kind of the opposite direction of tan, where tan, remember, your tan graph typically goes like this. Negative tan goes like this. Okay, this is a negative tan function. So where regular cotan does the opposite, it's also going to do the opposite. So our graph is going to go like that. In between those sets of asymptotes. Okay? And you can play around with this on Desmos to see it a little clearer. All right, let's move on to these inverse functions. As we talked about them in class, the easiest way to really deal with these particular functions is to draw them if needed and to recall your triangles, right? Your pi over 4 ratios and your so 1 is the smallest side, the smallest angle is actually pi over 6. This is pi over 3. It is incredibly helpful to you to have those two triangles drawn out for you. So sine inverse is asking what angle has a ratio of 1/2. So come over here, sine meaning opposite over adjacent. where is opposite over adjacent 1/2? Well, it has to come from this angle, right? Pi over 6. So the answer there would be pi over 6. Just get rid of what I highlighted. There is nothing else you need to do with that particular problem. But what if it were negative? Because the first one was positive, we were just working in the first quadrant. Because that's the other thing you got to think of. Okay, we have a restricted domain for our inverse functions. What we actually do is restrict the domain of the original trig function to get the inverse function. When we restrict the domain of sine, we restrict it from negative pi over 2 to pi over 2. In other words, we restrict it to quadrant 1, which is what we use in part A because it was positive, and quadrant 4, where sine is negative. So what we want here is this angle would be down here, and we would just simply call that one negative pi over 6. Not a problem. Okay? All right, I'm going to this. Let's take a look at the next one. We have cosine of sine inverse square root of 3 over 2. Okay, work inside the parenthesis first. Sine inverse of square root of 3 over 2. Which trig angle is going to give me a ratio where the opposite over the hypotenuse is square root of 3 over 2. That's going to be square root of 3, and it's positive, so you don't need to worry about any reference angles. We just use, or what quadrant it's in. It's just going to be in quadrant 1. So cosine this is just now pi over 3. What's cosine of pi over 3? Sine was square root of 3 over 2, but cosine is 1/2. Done. All right, let's move on. Sine of negative pi over 4. Well, we might want to draw this one. Negative pi over 4 is down here. When you take the sine, we know the ratio is 1/1 square root of 2. Put in the appropriate negative values. This one is negative. The one up top is positive. You can see from the graph. And we said that the hypotenuse was always positive. So sine of negative pi over 4 is opposite, which is -1. So we're just doing a regular sine of negative pi over 4. We're using negative pi over 4, putting it on the graph, using our basic triangles to get the sine of it. We're not doing any inverses because it doesn't say inverse. It just says sine of negative pi over 4. So sine of negative pi over 4 is -1 over square root of 2. We call that, we'll just leave it like that for now. Okay. So now I want cosine inverse of -1 over square root of 2. Now here's the problem. When we go to do our cosine function, now we are looking at an inverse function, and you need to think restricted domain. So now I'm restricted to where is cosine negative. The cosine is restricted from 0 to pi. We do not use that quadrant. So where would I get a -1 over square root of 2? Well, it's not going to be in quadrant 1. It's going to be out here where I have adjacent -1 square root of 2. This reference angle is pi over 4. Okay, the reference angle. Reference angle is pi over 4. I don't want the reference angle. I want the whole angle. So I got to do pi minus pi over 4 And pi minus pi over 4, of course, is going to be, which would be your answer, is 3 pi over 4 is the final answer. Okay, let's keep moving. Tan of tan inverse is 1. All right, so of these triangles, which one has a tan ratio 1? Well, that's going to be your pi over 4. So tan inverse of 1 is pi over 4, and tan of pi over 4 equals 1. So that is one that just kind of takes you right back. But make sure you go through the steps carefully, because if you were asked tan of tan inverse of -1, that's going to be very different. Because tan inverse of -1, see, in part E, I could just work in quadrant 1 because it was all positive and everything was good. But once I want tan inverse of -1, I need to think about that restricted domain. And tan, just like sine, restricts me to quadrants 1 and 4. So I have a -1 and a +1 for pi over 4. So tan inverse of -1 is actually negative pi over 4. All right. So tan inverse of -1 is negative pi over 4. And tan of negative pi over 4, in this case, does indeed bring you back to -1. All right. One more with our tans. Let's do tan inverse tan of 5 pi over 4. This is not an inverse function. You just got to draw your reference angle. Okay, 5 pi over 4 actually ends up over here. There's your pi over 4, because 5 pi over 4 is all that. So it's 1, 1. So it ends up being tan inverse of 1, because what's tan of pi over 4 is 1. But tan inverse of 1, because we are now working with the restricted domain, puts you back in quadrant 1's pi over 4. So that equals pi over 4. My point is, sometimes the tan and the tan inverses will cancel each other out, like these two did. They both became the same answer, -1, not a problem. In this case, tan inverse of tan does not go back to 5 pi over 4 because of that restricted domain. It actually ends up at pi over 4. Okay? All right. Number 4. Solve the right triangle given that a leg A is 3.7 and B is 4.3. Doesn't matter where you put it. And C is the right angle. This is clearly the right angle. We're going to call that C. Like I said, I don't care what you call A and B. I'll call this one 3.7 and that one 4.3. So if side A is 3.7, then angle A is across from it and angle B is across that, and C is there. You have to use everything you know to get this done. So where you can start is, well, you can start with the right triangle. That's probably the easiest way to start, and the Pythagorean theorem, right? You know that 3.7 squared plus 4.3 squared equals C squared. So grab your calculator. I'll do mine here. Squared. 13.69 plus and take the square root. I got 5.67. 5.67. Which, since everything, the other two angles are intense, we can round that to approximately 5.7 is perfectly fine. You're going to have to use a trig function to get one of these angles. So I'm going to just go with angle B. I'm going to use tan because I was given those two original ones, and I'm going to say tan of B equals 4.3 over 3.7. So then I got to use the inverse relationship. So I'll do, usually when we work with these application problems, we do put our calculators in degrees for those. So I need tan inverse of 1 point, and then we're using tan inverse because we're looking for the angle. And tan inverse. Don't forget, you usually got to use your second function to get the inverse. I got 49.3 degrees. We'll round it to 49.3. And then you can use the properties of a right triangle and do 90 minus 49.3. I got 40.7. Double check yourself. The smallest angle should be across from the smallest side, and that is exactly what's happening. So they're solving your right triangle. All right, part B. So you might have to sketch it out. I do believe on the test I give you pictures for maybe there's one application problem you got to do the pictures. It might be something like this. So a person on the ground, there's your person on the ground, hey, is flying a drone. So your drone's out here somewhere, right? Remember they tortured New Jersey a few months ago? Person on the ground is flying the drone. The drone is 50 meters above the ground. It's 50 meters. And the person is standing 80 meters horizontally from the point directly beneath the drone. Well, that makes sense. What is the angle of elevation from the person to the drone? So we're going to make a silly assumption that the person, is simply eye level. Their eye is on the ground. I'll make this easy. And we just want this angle. We want to know what that is. So you look at that and it's clear you've got a tan function. So tan theta equals 50 over 80. And just do exactly what we just did in the last problem. 50 divided by 80. So you're going to hit tan inverse of 0.625 equals your angle. Second tan that. It looks to be about 32 degrees. Okay. All right. Ship leaves port and sails on a bearing north 60 degrees east. So here's port, right? Here's your ship. You need a north line. And the ship is sailing east of that line, right? So the ship is sailing north. That's your north. The dotted line's the north. 60 degrees east. So that is 60 degrees. Apparently my battery is about to die, so we can right when I was in the last problem. Okay, again, we have our north line. Sorry, we are north 60 degrees east for 10 kilometers. So you're 10 kilometers here. It then changes direction and sails directly east for another 5 kilometers. Obviously, that's much shorter. Let's try to at least pretend to be somewhat. So it'll be half of what he did before. How far is the ship from port, and what is the bearing of the ship from port? Okay, so I got to start over on this problem and I'll update. You will see an updated part C on your Canvas because this particular problem is actually from another section that we haven't gotten to yet. So we're gonna change it up a little bit. So the ship leaves port and sails at a bearing north, right? And then 60 degrees east for 10 kilometers. That part is fine. So there's north, 60 degrees east. The question is going to be exactly how far is the ship from land? So this is our port. There's land. How far is it from land? We need this distance. So again, I will update the problem on the sheet in a little bit and actually put that in there. So if this is 60, that has to be 30 degrees because I got to reach up to 90. So you're looking at your angle. You need this side. You're given a hypotenuse, and you got to think about which trig function. It's simply going to be sine 30 degrees equals x over 10 kilometers. So it's 10 sine 30 equals x. Grab your calculators, make sure you are working in degrees. So sine 30, which you know is pi over 6, which you also know is a half. You don't even need a calculator, times 10 is 5 kilometers. So again, this will be updated than the one I showed you in class. We will go back to this original problem back when we do law of sines well after spring break. So good luck on your test. Please do make sure you show work, you show the trig functions that you're using for the application problems, even for solving the triangle. Remember, diagrams are incredibly useful to you while you are working out this group of problems. When I ask you to make the sketch, do label any asymptotes as equations, x equals, and do make sure you also label the intercepts. So for example, on that one. And then of course you know how to do these. You need an amplitude, a period, a phase shift. You've got to label on the tan or cotan, the tan functions. I need to see the intercept and I need to see the asymptotes, and the asymptotes labeled. And then for your sine and cosine, it's those 5 key points. Good luck on your exam, and I will see you all after spring break.